Hey, it's me, Miss Wesley again, and boy, am I excited as I look at the examples in the middle of page 2 of the Trig Packet because we are jumping straight into it today with the definitions of the 6 trig functions of any angle that you want. Now, I know people are coming into this course with differing backgrounds on what you've seen of trig. We are starting back again from the ground up to get this whole system back into our heads. So what are the 6 trig functions? Who knows about them? I see a little picture here of a right triangle with these important letters that are labeling the sides. You've got legs of x and y. That makes sense to me. X for a horizontal distance and y for the vertical height of that right triangle. And then r. I wonder why they're using the letter r instead of maybe like h for hypotenuse for this side right here, your terminal side of that angle, which ends at point P. Well, there's a reason for it. If I put this angle on what's called sometimes it's called a unit circle, but just like a circle here that comes out, wouldn't this distance be the radius of that circle? And that's why r is chosen. Now, before we fill all this crazy stuff in, I want to look at this fact about r. R is the hypotenuse of a right triangle, so it has to obey our old friend, the Pythagorean theorem. Always in these problems, the value of r squared has to equal x squared plus y squared. That's for sure. And if you solved this equation for r, you would get the square root of x squared plus y squared. Are you thinking to yourself, I don't know if you would be, but Miss Wesley, did you forget a plus or minus sign that should be out front of that square root because you're square rooting both sides? Well, actually, no, I didn't here because we're talking about r always being positive. X might be negative. X is negative in this picture because you've gone in the negative direction on the x-axis. And y could be negative as well if I were down in one of the other two quadrants. But r is always going to be greater than 0. R is always going to be positive, and you can use that square root to get it. How about all this notation here? Do not say sin, cos, and tan. Please, that's the last time I'm ever going to say it myself. It is the sine of theta. Technically, the trig function sine isn't spelled S-I-N. It's spelled S-I-N-E, and then S-I-N is the abbreviation. Cosine has an E on the end of it too, so cosine. And then T, or T-A-N, stands for tangent. That one's a pretty obvious one, right? And here are your abbreviations now. Just like, okay, so let's say I randomly give you a square root and I put nothing inside of it. That has no mathematical meaning. Or let's say trying to think for a second, we did logs. Let's say I take the log base 2 and I don't put anything next to it. It needs an argument here. It needs an x or an 8 or a 45. Same thing with these trig function values. Let's start with sine, cosine, and tangent. Sine without anything after it has no meaning mathematically. You need what's called an argument of that trig function, and it's going to be an angle measure. Has anybody seen this little symbol before? Was that used back in geometry? Well, I got to think to my trusty Greek alphabet because we've used a lot of the English alphabet letters to denote certain mathematical quantities, and now we're going into the Greek alphabet when we want to denote angles, and that's very common. Alpha is a common angle measure. Sometimes they'll just put alpha on the picture, or beta, right? The second letter of the Greek alphabet. Gamma, delta, epsilon, zeta, you got it all the way to this little circle with the line through it. It's going to be the Greek letter theta. And it is going to be our most commonly used variable to denote an angle in this entire unit, in this entire packet. So the sine, not by itself, sine of what? Of an angle of theta, right? Cosine of what? Of the angle theta, tangent of the angle theta. You'll see that afterwards. And you might remember when you see sine, cosine, and tangent, do you think so, ka, toa? We'll get to this, right? We know sine is the ratio of the opposite side from that angle in the right triangle to the hypotenuse. In this picture, you have theta actually being an obtuse angle, a quadrant 2 angle. If I put maybe like a little theta prime in here, this definition should follow SOHCAHTOA rules. So it's the ratio, sine equals just the ratio of two side lengths of that right triangle that got constructed of the opposite side to the hypotenuse. For us, instead of writing O over H, I want you to use the letters that are given on this picture, and I'd like you to write Y over R. We're going to use this as our definition. Sine of theta always equals Y over R. Cosine of theta. In SOHCAHTOA notation, it was adjacent over hypotenuse. We're going to always call it in our pictures in this unit x over r. So sine goes with the y. Think of the vowel sound. Sine, psi goes with y, right? Cosine goes with x. It's the other one. They're both over the radius. Tangent in TOA notation was opposite over adjacent. We will call it y over x. And consequently, I know I'm getting ahead of myself. If you divide this blue fraction by that blue fraction, you actually get this blue fraction here. Y over r divided by x over r makes those r's cancel and you get tangent. It's called a quotient identity, the sine over the cosine. What's great is that once you have these three, it is not hard to get these three because all you have to do is flip them. These are your reciprocal identities. Reciprocal. So if sine is y over r, cosecant, its reciprocal is going to be r over y. That's cosecant, CSC. If cosine is x over r, let's flip that to get secant, its reciprocal, so r over x. And cotangent is the reciprocal of tangent, so we'll make it x over y. Again, especially here, x and y cannot be 0 in these three definitions because in this one, y can't be 0. You just can't have 0 on the bottom of the fraction. But I want to keep this in mind as we try an example like number 10. Here's where this stuff starts getting pretty exciting. Step 1, okay, so it says the terminal side of angle theta in standard position passes through the given point. Can you find the values of all 6 trig functions? So sine, cosine, tangent, and then the reciprocals, cosecant, secant, and cotangent. Well, first, let's plot the point 8, 15. What quadrant is that going to fall in? A positive x and a positive y. We're in quadrant 1. So your initial side is always along the positive x-axis. The terminal side, can you just draw me any angle that's over in quadrant 1? It doesn't need to be drawn perfectly or to scale. It really does matter, though, that we are in the correct quadrant. And technically, if the point here is at 8, 15, and if I create, like when you see this picture, does any kind of right triangle pop out at you? Or perhaps could you see 2 different right triangles? Because I see 2. I feel like there's 2 ways I could connect this terminal side. I could connect it horizontally over this way and make a right triangle. Or can you actually draw this one? I could connect it vertically down to the x-axis and make a right triangle. You'll notice in the picture above, this was a quadrant 2 angle, but you always connect down to the x-axis. It's as if you're ignoring the y-axis, it's not even there, and you always, no matter what quadrant you're in, you'll make your right angle with the x-axis. So do we know 2 of the 3 sides of this right triangle? Because if we know 2 of them, we have a way to get the 3rd side. Well, we do. We've come over x equals 8. We've come over 8 on the x-axis, positive. We've come up 15 on the y-axis, and we're just missing r. We're using that letter r to pretend like we have a circle, and this is the radius here. So let's do a little side work underneath. Let's use Pythagorean theorem. R squared is always going to equal x squared plus y squared. So r squared equals, well, 8 squared, 64, plus 15 squared, 225. To get a total r squared of 289. And we square root to get 17. I'm just a little curious. Anybody in the crowd know that it was going to be 17 because they saw those other 2 sides? There's such thing as a special right triangle, and it's got these sides that are integer lengths or whole number lengths. So this is called an 8, 15, 17. Right triangle. It's not one that you need to have memorized. A 3, 4, 5, I think you might have seen before. If you have legs of 3 and 4, hypotenuse is always going to be 5. And a 5, 12, 13 you see coming up a lot. This is just another example of a special one, but either way, if we're not remembering that the missing side is going to be 17, we can use Pythagorean theorem to get it. All right, now find the values of the 6 trig functions. I think we've got everything we need. So I'm going to set it up with the first 3. Sine, I always put cosine right underneath, and then tangent being the 3rd one. I like to get these out of the way with first. Then when I have to go and get the reciprocals, it's easy. You can just flip the answers you got. So sine, according to the definition, sine always equals the y value over the r value. So here, y is 15, and r we just got as 17. You have your sine. Cosecant, if you want to just get this out of the way, will be 17 over 15. It'll be the reciprocal. All right, what is the cosine of this angle? You know what I forgot to do? I forgot to put theta on the picture too. So theta is your angle from the initial to the terminal side. We'll put theta in there. Okay, now back to business. Cosine, x over r. So 8 over 17. And its reciprocal secant is 17 eighths. Okay, last but not least, tangent. Y over x, so 15 eighths. And then what is its reciprocal? So COT, cotangent of theta, don't forget to put the theta after it, will be 8/15. So we can call this one finished. For now, you might be thinking, okay, whoa, that was a lot of writing. We figured out a bunch of trig function values. Well, what good does that do us? We got to take this in baby steps. This is just an intro to trigonometry. For now, we found 6 ratios of sides of that right triangle. Moving forward with trig, little by little, we'll be able to use identities and formulas to put these numbers to use. But for now, just getting our bearing with finding those trig function values. Let's look at number 12. 12 says, same directions. Can you figure out which quadrant we should be in if your terminal side falls through this point? So negative 2 square root of 3 means on the x-axis we're negative. Positive 2 for the y, we are up on the y. You need to draw yourself a quadrant 2 angle for this one. Also remember, we're going to be talking about signs of the trig function values as well. In that last problem we just did, we were in quadrant 1 and we got all positive values. Here, what quadrant are we in? We're in quadrant 2, keep that in mind. And I want to pay close attention to how many positive and how many negative answers we get. So for that reason, when I label the sides of this, I'm just going to do this for my own personal help. I'll make x equal to negative 2 square root of 3 like it says in the problem, and y is going to equal 2. So again, first order of business, let's find r. If it doesn't pop out at you, we can use the Pythagorean theorem. Let's do that. Okay, so r squared equals x squared plus y squared. So negative 2 square root of 3 squared plus y squared, just plus 2 squared. So r squared equals, let's square both parts. This will go positive, 4 times 3 plus the number 4 equals 16. That means r, don't worry about a plus or minus, it's just going to equal the whole number 4. All right, let's give this a try. All 6 trig functions. So number 12, the sine of theta, and I should put, again, I keep forgetting to put theta on the picture, the cosine and the tangent, and we'll flip those to get their counterparts. Tangent. Okay. So sine, again, by definition on the last page, we're going to use y over r. So y is 2, and r we just got as 4. We'll say the sine is exactly a half. Cosine, x over r. So x is negative 2 square root of 3 divided by the 4 that we got for r. So why don't we reduce this one as well and get negative 3 square root of 3 over 2. Tangent, y over x, so 2 over negative 2 square root of 3. This is the first time we also should be thinking about rationalizing denominators here, meaning getting any radicals out of the bottom of the fraction. Well, we can do that by multiplying top and bottom by the square root of 3. And another thing I can do in the meantime is there's no reason to have those 2's on the top and bottom. So like in the first 2, we can reduce that and make these 1's. Here's what you get. You get square root of 3 up top. On the bottom, negative, this times itself gives you a 3. There is your exact value for tangent. Okay. Now we want to flip these. Some are quick. Cosecant is the reciprocal of sine, so we'll just get 2. Cosine's reciprocal is secant. If we flip this, we'll just have to rationalize. So negative 2 over square root of 3, rationalize, you get negative 2 square root of 3 over 3 for an exact value. And lastly, cotangent, tangent's reciprocal. I say flip this original blue version so you don't have to worry about rationalizing instead of flipping this final answer. So the original was like a 1 over negative square root of 3. Let's flip that back up when all said and done to just get the negative square root of 3. So that was some good practice. Again, I said keep in mind the signs that we're getting in these problems too. The one other thing I want to make sure to show you before we go is skip down. We're going to come back to 12 because 12 is a great question. But look at these signs of trig function values. I want to teach you an acronym before I leave. The sine, cosine, and tangent in each of the quadrants, the SIGNs, the signs of them are given. All trig functions are positive in quadrant 1 because if you look at those definitions, x, y, and r are all positive. So I'm going to put a big A here. Only sine and its reciprocal are positive in quadrant 2. I'm going to put an S here because in quadrant 2, only the y is positive and the r, right? And cosine and tangent have to do with x. They're going to be negative. In this quadrant, quadrant 3, you have a negative x and a negative y. meaning in quadrant 3, only tangent is going to be your positive one, and it's reciprocal. So tangent always is positive in quadrant 3, and then in quadrant 4, cosine and its reciprocal are positive. We're going to pick up with this shortcut in the very next video. So I'll talk to you soon. Have a good part of your day.